Hello everyone, in this video I'll be teaching you how we can compute binomial coefficients. The reason why I chose this topic is because most websites use binomial coefficients computation only using dynamic programming, and that is very inefficient because that won't help us to compute NCR for n and c, n and r being greater than or equal to for example 10 to the power of 6 or 10 to the power of 5, because that method only works when n into r is less than or equal to 10 to the power of 6. So basically when n and r are both about 1000, then only that method of using dynamic programming to compute NCR works, otherwise it doesn't work. And a lot of recent Codeforces problems, specifically yesterday's or day before yesterday's Codeforces contest and another recent Codeforces contest, both being Div 2 Cs, so quite early on in the contest, require you to compute some combinatorics operation, and over there I realized that we needed to use binomial coefficients as a step in the solution. So for those of you who don't know how to compute binomial coefficients efficiently, will automatically have no chance to solve these div 2c problems, and that's why I'll be explaining this important concept. So basically the binomial coefficient NCR is given by the formula n factorial divided by n minus r factorial into r factorial. And notice we always take this number modulo 10 to the power of 9 plus 7. So let's say it's modulo some prime number p, and where p is either 10 to the power of 9 plus 7 as in this problem, or it's another prime number. So we are assuming that p is a prime number for an important reason which I'll mention later in this video, and we need to compute this efficiently. The only reason why there's a difficulty in computing this efficiently is because we are dividing the number by the product of two numbers, and we can't do that efficiently, or basically we can't do that at all. We can't use division when we are dealing with mod some number and like using normal tools. And to solve that, we first need to understand how we can do division modulo a prime number. So let's say I want to compute the value of 1 by x mod prime number. So let's say I denote x inverse by 1 by x. So x inverse is 1 by x mod some prime number, and I want to compute this value. So to compute this value, which is basically 1 by x, I'll use a theorem called Fermat's little theorem. So Fermat's little theorem basically tells us that x to the power of p minus 1 is congruent to 1 mod p when x is not 0 mod p. So basically this holds for most values of x. When x is 0 mod p, then you can clearly see that 0 to the p minus 1 is just 0, which is not 1. So that's a trivial case which is not taken care of in Fermat's little theorem. But otherwise, this holds for any x and any prime number p. And the advantage of this theorem is that we can conclude that x to the p minus 2 is congruent to 1 by x mod p. And this basically holds because we divide by x on both sides, and that basically tells us that 1 by x is actually x to the p minus 2. So this is the key idea. So even if you don't understand some of these modular equations, you can just take it for granted that x to the p minus 2 is congruent to 1 by x mod p. So that's the crux behind how to compute this efficiently, and afterwards is just simple algebra. So then afterwards we know that to find n factorial divided by n minus r factorial into r factorial, we will just take n factorial the same, and we need to compute r factorial. So we need to compute 1 by r factorial. So for computing 1 by r factorial, we can basically replace 1 by r factorial with r factorial to the p minus 2, and we can replace n minus 1 by n minus r factorial. So we can replace this number by n minus r factorial to the p minus 2, and basically this is how you compute numbers, binomial coefficients, basically a modular prime number p. And an important thing to note over here is that you need to have the factorials pre-computed. So pre-compute all n factorial and all r factorial. That can be done easily in one loop, and use binary lifting or basically binary exponentiation to compute this power efficiently, and I'll be showing you in the code how we can exactly do this. Also, you can submit it on CSES for just verification purposes. Now I'll show you the code implementing the same idea. So I have a global variable factorial which represents the factorial of all numbers. I have the binary exponentiation function which returns a to the power of b efficiently using binary exponentiation. So basically this takes log and log b time where b is the base, and basically like this is some simple code which does it. So basically if b is even, we return the square of a to the b by 2. Otherwise, if b is odd, we return the square of a to the b by 2 into a. This is a trick which you can use, and if you didn't already know that, then like just understand this piece of code. It's quite simple. And now I have the inverse function. So basically inverse of some number x will give x to the mod minus 2, or basically x to the p minus 2, where p is the modulus. And the reason for this is what I just said, because x to the p minus 2 is 1 by x mod p, and that's what I return. Then the binomial coefficient of a choose b is given by a factorial divided by b factorial divided by a minus b factorial, and instead of dividing I use multiplying by inverse, and that's basically the whole binomial coefficient function. The rest is just standard code. I compute factorial using this recurrence, and for each test case I print binomial a choose b, and now you can see that this code does get accepted. So this is the exact same code which gets accepted, and basically this is like some knowledge which you should have whenever you're going to a Codeforces round or any other competitive programming competition, because it can be extremely useful, especially since Div 2 Cs are also involving some combinatoric stuff. And this pre-written code will basically help you compute A choose B efficiently. So that's all for this video. If you like this video, don't forget to give it a thumbs up. Also, if you have any other video suggestions, or if you want me to make a video on any specific tutorial or any specific topic, do leave them in the comments down below. Thank you.